Hello, everybody, and welcome to Algebra tape number 7. And we're going to be going over the homework assigned on section lesson 28 and 29. Um, Also, I want to remind you, I'll be on Friday, I will be bringing you your second algebra test, and it will go up through section lesson 29. The last homework section here. So please look over the previous sections that will be on this test and make sure you come in with any questions on Friday that you might have about any of it. Okay? So, um, uh, the homework in lesson number 28. Okay, lesson number 28. Complex fractions. A complex fraction is simply a fraction that has a fraction in the numerator or denominator, or both, and you have to get rid of the fractions. You have to make it a simple fraction, which is something over something else, not a fraction over a fraction or a number over a fraction. Complex fraction has a fraction in numerator or denominator. So 1/2 over 7 is a complex fraction. 1/2 over 7/5 is a complex fraction. 1 over 7/5 is a complex fraction. Here I have a fraction in numerator and denominator. Here I have a fraction in the denominator. That first one I had up there. Here I have a fraction in the numerator. None of those three are acceptable. In all three cases, you have to get rid of the unnecessary fractions and end up with just a simple fraction, which is just a quantity divided by another quantity. Okay? And in section in section 28, I asked you to do 3 through 21 odd, and then 26 and 27. So, first problem, number 3. Word problem, the number of girls in a class was 1 less than 3 times the number of boys. There were a total of 15 students in all. How many were boys and how many were girls? Again, you can do this problem in 1 or 2 variables, and again, I highly suggest, if you can, do it in terms of 1 variable. It's just less margin of error. So if I let x equal the number of boys, then 15 minus x is the number of girls. It said there were a total of 15 in the class. And it said that the number of girls was 1 less than 3 times the number of boys. So I can do this also in this way. This number, 15 minus x, is 1 less than 3 times the number of boys. Well, if the boys is x, 3 times that is 3x, and 1 less is 3x minus 1. Excuse me. I had to plug in. And there's your equation. Add x, you get 4x is equal to 16. X equals 4. Therefore, there are 4 boys. And 4 from 15 is 11 is girls. 4 boys, 11 girls. That's one way to do it. There are others. You could have done it in 2 variables if you wanted. Let x equal the girls or boys. Let y be the other. X plus y is 15, and then you can get your second equation would be the girls is 1 less than 3 times the boys. This one's just as simple to do in 1 variable. 11 girls, 4 boys. Hopefully you understood one of those ways. Number 3. Number 5. Arthur found that for every 200 peasants, only 10 had seen a Dane. If there were 150,000 peasants in the kingdom, how many had never seen a Dane? Well, if with 200 people, only 10 had seen a Dane, that means 190 had not. You can do this either in terms of the total to have seen or have not. Since they asked you how many of the 150,000 have not, I'm going to do it in terms of how many people have not seen a Dane. So if 10 had seen a Dane, that means 190 had not seen a Dane out of 200. So you're looking for the number that haven't seen a Dane out of the 150,000. So there's your proportion. 190 over 200 is equal to x over 150,000. Cross multiply 190 over 200 times 150,000 equals x. You can do that by simplifying. It's just as simple. If you have a calculator, plug it in the calculator, and you should have found x is equal to 142,500. So out of the 150,000, 142,500 of them have not seen a Dane. If you did this in terms of the number of people that had seen a Dane, you would have gotten 7,500 had not seen the Dane. Then you would have had to have subtracted that number from 150,000, and you still would have gotten 142,500 out of the 150,000 had not seen a Dane. Number 5. Number 7 was a long division problem. And again, with long division, to not make an error, a sign error, if you're missing a power of the variable, I've told you, please insert 0 times that missing power, and it will make for a lot less confusion. All right, you're dividing x cubed minus 7. So I've got x cubed plus 0x squared plus 0x minus 7. And it said divide that by x minus 5. The object is to always remove this first term. X times what gives you x cubed? X squared. X squared times the whole quantity is x cubed minus 5x squared. Enclose in parentheses and subtract. Again, the object is to always remove the first term, which we do. X cubed minus x cubed gone. 0x squared minus a minus is positive. 5x squared. Bring down your next power of x. X times what gives me 5x squared plus 5x. You multiply positive 5x times the whole dividend, you get 5x squared minus 25x. Enclose in parentheses and subtract. First term disappears. Negative and negative is 25x minus 7. X times what? X times 25. And you get 25x. 25 times negative 5 is minus 125. Enclose in parentheses and subtract, and you get positive 118. So you write that as plus 118 over x minus 5, what you're dividing by. Okay? And that is your quotient. Or you could have said a remainder of 118, same thing. Hopefully everybody has an inkling of an idea. Again, we're not going to do long division a whole lot, but they want you to understand it. Number 9 said factor the greatest common factor out. You've got 4x squared y cubed p cubed minus 16 x squared y cubed p minus x to the 4th y cubed p to the 4th. All right, the greatest common factor is the number that every one of these has, a number or variable raised to a power that's common to all of them. Well, I have no numerical common factor because this one has a exponent or a numerical coefficient of minus 1. So the 4, 16, and 1, the only common factor is 1. I have an x squared, and an x to the 4th, so I can bring out an x squared. They all have a common factor of x squared. I have a y cubed, and a y cubed. I can bring out a y cubed. I have a p cubed, a p, and a p to the fourth. The factor common to all of them, the highest factor, is p to the first, or just p. You then multiply by what's left. I've got a 4, I've got the x squared, I've got the y cubed, I need a p squared. The next term, 16, x squared, y cubed, p, it's just minus 16. If I multiply this times minus 16, I get what I started with. Minus x squared, x to the fourth, I need an x squared. I've got a y cubed, gone. I've got a p, I need a p to the fourth, so it's p cubed. This is the factored form of what we started with. The greatest common factor was x squared, y cubed, p. And that's all I can do with problem number 9. Number 11. Number 11, they asked you to factor completely. And the first step is always the greatest common factor. And here you have negative 8a minus 7ax plus ax squared. Now, a couple of ways to go about this one. Generally, kids have it easier if the squared term is first and positive. So I could rearrange these terms and start with ax squared minus 7ax minus 8a. This is exactly the same as what's above it, but I now have the x in descending power. X to the second, x to the first, x is gone, or x to the 0 if you want to think of it that way. And again, you don't have to do this, but generally kids find it easier to factor if the squared term is first and positive. In this case, it's first and positive. Take out your greatest common factor, which is an a, and you're left with x squared minus 7x minus 8. If you stop there, you're one step short because this trinomial is also factorable. A times x and x, 8 and 1. I want a negative 7, so it's minus 8 plus 1. Check it. X times x, x squared. Outside, inside. Positive x minus 8x is minus 7x. Negative 8 times positive 1 is negative 8. This is the completely factored form of this. If you did not rearrange your terms, you might have had a little bit of difficulty, but it's basically still the same problem. Factor out an a. You've got negative 8 minus 7x plus x squared, which is a times it's still negative 8 and 1 plus x plus x. That is exactly what we had before. The only difference was instead of negative 8 plus x, we had it written as x minus 8. This and this are the same. And when you multiply these out, if you turn that one around, again, addition is commutative. 1 plus x is the same as x plus 1. So, whichever way you did it, you would have ended up with this, hopefully. That is the correct answer. A times x minus 8 times x plus 1, or you could have written it this way. A times negative 8 plus x times 1 plus x. These are equivalent. And that is completely factored. Okay? That was number 11. Number 13. Number 13 is also a factoring problem minus a squared minus a squared x squared minus 2x a squared. I would recommend, and again, there's a couple ways you can do this problem. I would recommend, since all the terms are negative, to bring out a negative a squared. And if I bring out a negative a squared, this becomes 1 plus x squared minus 2x. And then rearrange your terms. Minus a squared times x squared minus 2x plus 1. When you're trying to factor a trinomial again, it's generally easiest or easier if you have the variable in descending order of the power. 2, 1, gone. At this point, I can now factor. Since the last term is both, I'm going to have one negative and one positive term, or excuse me, they're both negative. Since the last term is positive, and there's only one way to factor 1, 1 and 1. X minus 1 times x minus 1 gives me x squared minus x minus 2x, minus 1 times minus 1 is plus 1. And you could write that negative a squared times x minus 1 squared. That is also the same as that. Anytime you multiply like quantities, you can write it as a quantity squared. This is the completely factored form of my original. Had you not factored out a negative a squared, let's leave this answer, make sure we get the same thing. Suppose you just factored out an a squared. If you just factored out an a squared, you've got minus 1 minus x squared minus 2x. And I have a feeling if you had it this way and you didn't make your x squared term positive, you're going to make a factoring error. But let's just arrange the terms. All right, put the squared term first, the 2, 1, gone, exponent, in terms of the exponent. And again, I have a feeling people would factor this incorrectly. X and negative x. That's the only way to factor negative x squared. One's got to be positive, one's got to be negative. I've got to have a 1 and a 1. And since the last term's negative, I've got to have 1 positive, 1 negative. Does that work? X times negative x is negative x squared. X times negative 1 is negative x. 1 times negative x is negative x minus 2x. 1 times negative 1 is negative 1. So that works. How in the heck does this become that? Well, multiplication is commutative. So I could write this a squared times x plus 1. I could factor a negative 1 out of this, and it becomes x plus 1. Negative 1 times x is negative x. Negative 1 times 1 is negative 1. Since multiplication is commutative, I can multiply that times that. I take this back. What did I do? I got a sign error in here. Anybody see my sign error? X times x, negative x squared. Is this equivalent to this? And the answer is yes, because when you bring this out front, you get negative a squared times x plus 1 squared. There you go. So it's the same thing. Okay? It was a whole lot easier to do it this way. Factor out a negative a squared, and it then turns everything positive right off the bat. You get x squared, x squared plus 2x plus 1. And then it becomes a whole lot simpler to factor. Okay? That's number 13. Number 15. Number 15, radicals. 4 root 27 minus 3 root 48 plus plus 2 root 75. Alrighty, a radical is not simplified if the radicand, the number under the radical, has a perfect square as a factor. And in all three of these radicals, there are factors under the radical that are perfect squares. This is 4 times 9 times 3 minus 3 times 16 times 3 plus 2 times the square root of 25 times 3. 9 is a perfect square, 16 and 25 are perfect squares. The square root of 9 is 3, it comes out. 4 times 3 is 12. Square root of 16 is 4, it comes out. Minus 3 times 4 is minus 12. Square root of 25 is 5, comes out. 5 times 2 is 10, root 3. These are now like radicals. Simply combine them by combining the numerical value in front. 12 minus 12 plus 10 is 10, root 3. So number 15 simplifies to 10 times the square root of 3. Hopefully everybody understood that. Number 17 is a scientific notation problem. And again, scientific notation was really, really useful before calculators came along. You could take a rather complicated problem, which this would be if you didn't have a calculator, and you can make it doable fairly simply by changing all of these using scientific notation. 0.00077 is 7.7. Scientific notation, you always want to have a number between 1 and 10, greater than 1, less than 10, times 10 to some power. And in this case, I'm going to have to move the decimal 5 units, or 1, 2, 3, 4 units to the right. So it's times 10 to the 4th. 7.7, 10 to the negative 4th. That means I'm moving the decimal 4 units that way to get to 0.00077. Times 10 to the negative 3 times 40 times 10 to the 6th. 40 is 4.0 times 10 to the 1st times 10 to the 6th. So there's the top written out in scientific notation. The denominator in scientific notation, 0.00011, is 1.1 times 10 to the negative 4 times 10 to the 5th times 140,000 is 1.4 times 10. In that case, you would have to go 1, 2, 3, 4, 5 times 10 to the 5th. All right? So now, look what I can do. Well, 1.1 and 7.7. 1.1 goes into 7.7 7 times. That's easy enough to do. Let's leave these alone because things are going to get real simple here in a second. So this becomes 7 times 10. Negative 4 minus 3 is minus 7 times 10 to the 7th, which is 10 to the 0, which is 1. So my numerator simplifies to just 7. And I've gotten rid of this 1.1. My denominator, negative 4 plus 5 plus 5 is 10 to the negative 6. And I have that 1.4. Okay? Now, excuse me, 10 to the 6, positive 6. 4 plus 5 plus 5 is negative 4 plus 10, or 6. Hopefully you didn't stop there, because 7 goes into 1.4 how many times? It goes in 0.2 times. 7 into 14 is 2, so 7 into 1.4 is 0.2. So this is the same as saying 1 over 0.2, which is 2 times 10 to the negative 1, times 10 to the 6th. So I get 1 over 2 times 10 to the 5th. I can leave it that way, or that is the same as saying 2 times 10 to the negative 5. Okay? I think I left something out. I'm missing something. Ah, I see it. I'm sorry. I left that out. My numerator becomes 7 times 4. There's a 4 there. Okay. 0.2 goes into 0.4. 0.2 times. Over 10 to boop, 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 boop. Wait a minute. All right, I messed this whole thing up. Let's go from here down. All right, this whole thing simplifies into, forget that right there. Leave that alone for a second. It's 7.7 times 4 times 10 to the 4 and 3 is 7. 10 to the 7th, so it's 10 to the 0. My denominator becomes 1.1 times 1.1 times 1.4 times 10 to the 6th. Okay. That goes into that 7.4 over 1.4 reduces to what? 7 goes into 1.4, 0.2 times. 0.2 goes into 0.4. That's like saying 4 over 2, so that reduces to 2. So this whole thing becomes 2 over, I still have a sign error somewhere. So see these really simple problems. You're lucky you have calculators. Now, I did this whole thing out last night. Let me start this whole thing over because I wrote something wrong. 7.7 times 10 to the negative 4 times 10 to the negative 3 times 4 times 10, that's 40, times 10 to the 6th, all over 1.1 times 10 to the negative 4 times 10 to the 5th times 1.4 times 10 to the 5th. All right, let's simplify the numerator. 7.7 times 4, leave those alone for right now. 4 minus 3 is negative 7, positive 7, 10 to the 0. My numerator simplifies to 7.7 times 4. The denominator, 1.1 times 1.4 times 10, negative 4 plus 5 plus 5 is 10 to the 6th. Okay, now start simplifying. 1.1 goes into 7.7 7 times. 7 goes into 1.4 0.2 times. So my numerator is a 4. 0.2 I can change to 2 times 10 to the negative 1 times 10 to the 6th. 2 goes into 4 twice. 10 to the negative 1 times 10 to the 6th is 10 to the 5th. So my answer is 2 over 10 to the 5th, or if you want, 2 times 10 to the negative 5. Either or. Again, we're not going to do a lot of these. You're going to see them in like these first few sections, and then they're going to disappear. 2 times 10 to the negative fifth, or 2 over 10 to the fifth. Number 19, 3 over 4 root 15. All right, again, our rules of radicals, you can never have a fraction that has a radical in either the numerator or denominator, or excuse me, in the denominator. You have to what is called rationalize the denominator. And in order to rationalize the denominator when you have a radical, you have to multiply by whatever you need to make that radical in the denominator disappear. You multiply, and you want to multiply by the smallest thing that will make the number under the radical a perfect square. Well, 15 times 15 is a perfect square. 15 times 15 is 125, so I need to multiply by radical 15 over itself. And the reason I do this, anything over itself, with the exception of 0 over 0, is 1, and 1 times any number doesn't change it. So my numerator becomes 3 radical 15. My denominator becomes 4 times root 15 times root 15 is 15. 15 times 4 is 60. And this can be reduced to radical 15 over 20. And if you wish, write it this way, 1/20th times radical 15. These are equivalent. Either way is perfectly fine. Root 15 over 20, or 1/20th times the square root of 15. I hope you understand these are the same. Rationalizing the denominator. Number 21. Number 21, you started with 2x over x squared plus 2x plus 1 plus 3 over x plus 1. All right, when you are asked to simplify fractions, when you combine fractions by addition or subtraction, you have to have a common denominator. So what you had to do here was realize this is x plus 1 times x plus 1. This is a problem that we did a little while ago. X plus 1 times x plus 1 can be written as x plus 1 quantity squared plus 3 over x plus 1. My lowest common denominator is x plus 1 quantity squared. Lowest common denominator is all the denominators, all the factors, the highest degree they show up. X plus 1 squared is higher than just x plus 1. So I now have, I've got to get all of my denominators x plus 1 squared. So this is 2 over x plus 1 squared plus 3 over x plus 1. In order to make that an x plus 1 squared, I need to multiply by x plus 1 over x plus 1. I now have a common denominator. X plus 1 squared, x plus 1 times x plus 1 is x plus 1 squared. And I can combine the two numerators. 2 plus 3 times that is plus 3x plus 3. So in simplest form, I get 3x over plus 5 over the common denominator, x plus 1 squared, and I cannot go any further. That is those two fractions added together and simplified. 3x plus 5 over x plus 1 quantity squared. Number, whatever that was, number 21. Okay. Did I write that correctly? No. X 2x now it's correct. Be careful. Stupid little mistakes like that will cost you. And I make them all the time, if you haven't noticed. So be careful, especially on testing purposes, especially on standardized tests. A slight mistake like that, I guarantee that other answer would have shown up as one of your choices. You're going to fill in the bubble and move on. Unfortunately, it'll be incorrect. Make sure you don't make a crazy little error like change that from 2x to 2, which is what I did. And all these mistakes that I make, I always do them on purpose, just to make sure you're paying attention. Number 26. Number 26 said solve 2x over 3 plus x minus 3 over 5 equals 1. All right, now you have a fractional equation, and the easiest way to solve a fractional equation is find the lowest common denominator and multiply every term on both sides by the lowest common denominator, eliminating the fractions. So in this particular case, it's fairly simple. The lowest common denominator is 15. So I'm going to use super parentheses, and I'm going to multiply every term on both sides of the equation by 15. 3 goes into 15 5 times. 5 times 2x is 10x. Plus 5 goes into 15 3 times, so it's 3 times the whole numerator. 3x minus 9 equals 15. 15 times again. 15 times this, you get 30x over 3, which is 10x. 15 times that. The 5 goes into 15 3. 3 times the whole numerator. 3x minus 9 equals 1 times 15. 10x plus 3x is 13x. Add 9 equals 24. So I get x is equal to 24 thirteenths, which is irreducible. Leave it at that as a top-heavy fraction reduced to lowest terms. Okay. Hopefully there are no questions. And number 27 was your last problem. 4 1/3 minus 2 1/5 x equals negative 3/10. All right, now, this is a fractional equation, but before I can solve, you should change your mixed numbers into fractions. 4 1/3, 3 times 4 is 12 plus 1 is 13 thirds. Minus 2 1/5 is 5 times 2 is 10 and 1 is 11. So this is minus 11 fifths x equals negative 3/10. The lowest common denominator between a 3, a 5, and a 10 is 30. Again, that's 3 times 1, so just 5 times 1 and 2 times 5. So the lowest common denominator is 3 times 5 times 2, which is 30. So enclose in parentheses and multiply every term by the lowest common denominator. 30 times 13 over 3, 3 goes into 30 10 times. 10 times 13 is 130. 5 goes into 30 6 times. 6 times negative 11x is negative 66x. 10 goes into 30 3 times. 3 times negative 3 is negative 9. Okay, 130 minus 66x minus 9. Solving. Add 66x to both sides, just so we get rid of the negative. Add 9, 139. X therefore is 139/66. And that is prime. That is your answer, 139/66. There are no common factors of 139 and 66. 139, I believe, is prime. Okay, 139/66. All righty. Your next set of homework was from lesson 29, which we talked about more motion problems. The only difference now was instead of starting at the same spot and going to the same spot, uh, we have things going in different directions. But it's still the same thing. With any motion problem, use that little box, distance equals rate times time, and you can figure out what you're missing and what you're looking for. If I have somebody going that way and somebody going the other way, eventually they're going to end up that far apart. So instead of starting and ending at the same place, they're going in different directions, but you might know what the whole distance is that they are apart, or you might be asked how long will it take them to get that far apart, but it's still essentially the same problem. Distance equals rate times time. Okay? So on lesson 29, the first one, number 1, it said Patton walked for 76, walked part of the 76 miles to the site of a battle and rode the rest of the way on a caisson, which is a cart pulled by a horse. He walked at 4 miles per hour and rode at 15 miles per hour. If the total time of the trip was 8 hours, how long did he walk? Again, distance equals rate times time. Walk, ride. I know that walking his rate was 4. I know that riding his rate was 15. I know that the total time of the trip was 8 hours. So if I call his time walking x, that's I made that the variable because it said how long did he walk. So if I let x equal the time that he walked, when I solve for x, that's my answer. And it said that the total time walking and riding was 8 hours. So if I'm going to walk for x hours, then the rest of the time, 8 minus x, not x minus 8, 8 minus x is the total time that he rode. Distance is equal to rate times time, so I walk a total of 4x miles, and 15 times that is 120 minus 15x. 120 minus 15x is the time riding, and I know that these two distances added together were the total trip, which was 76 miles. So 4x plus 120 minus 15x has to add up to 76. So 4 minus 15 is negative 11. Add the negative 11x. Subtract 76 from 120. You get 44. Divide by 11. X is equal to 4. He walked for 4 hours and he rode for 4 hours. Does that work out? Well, if I walk for 4 hours, 4 times 4 is 16. 15 times 8 minus 4, 15 times 4 is 60. 60 plus 16 is 76. He's gone a total of 76 miles. Okay? Number 1. Number 3. At 5 p.m., Roger whizzed off from asteroid. 1 hour later, Marianne whizzed off from asteroid. They go in opposite directions at a speed of 4, and her speed, Marianne's speed, was 400 kilometers per hour, less than that of Roger. If they were 7,900 kilometers apart at 11 p.m., how fast did each travel? All right, I got Roger and Marianne. I know that Roger's speed is what we're looking for, and Marianne's. So I can let x be either his or her speed. I'm going to do it in terms of Roger. If I call his speed x, her speed is 400 kilometers per hour less. X minus 400. All right, now, it said that Roger left at 5 p.m. and the question asks, how far apart are they at 11 p.m.? Well, from 5 to 11 is a total of 6 hours. So Roger was zipping along for a total of 6 hours. Mary Ann left 1 hour later. Well, if he traveled for 6, that means she's going to travel for a total of 5 hours, 1 hour less. She left an hour later. So his total distance was 6x. Her total distance is 5x minus 2,000. And what do I know about these two distances? Again, one starts here going that way, one starts here going that way, and it said that at 11 p.m. they were 7,900 kilometers apart. So these two distances added together, 6x plus 5x minus 2,000 is equal to 7,900. So 11x is equal to 9,900. Divide and you get x is equal to 9,900 over 11, which is 900. So Roger's speed was 900 kph, and Mary Ann's speed was 400 less, 500 kph, or Mary Ann's speed. All right? Hopefully everybody understood that one. All right, number 5. Number 5 said, for every 130 squirrels in the forest, there were 156,000 good places for them to hide. If there were a total of 3,250 squirrels in the forest, how many good places were there for them to hide? Well, for every 130, there are 156,000. And they said for a total of 3,250 squirrels, how many good places were there for them to hide? So there's your equation. So you get 130x is equal to 3,250 times 156,000. Therefore, x is going to be 3,250 times 156,000 divided by 130. Again, you could just do it out longhand if you want. Plug it in a calculator, make it a whole lot easier. You get 3,900,000. There are 3,900,000 places for those 3,250 squirrels to hide. Okay. That was problem number 5. Okay, number 13 was your next problem. Number 13 said they wanted you to simplify x squared plus ax squared all over x squared. Well, your numerator, you could factor out the common factor x squared, and you're left with 1 plus a over x squared. I now have all multiplication in numerator and denominator, therefore I can cancel common terms. Anything over itself is 1. So this simplifies to 1 plus a. Okay. A common error, people would do this. They'd go, oh, x squared cancel, and you get 1 plus ax squared. Almost, but no banana. You can only cancel from numerator and denominator when you have all multiplication in the numerator and the denominator. Okay. Number 17. Number 17, a complex fraction m over x divided by m plus x over x. Again, realize this is m over x divided by m plus x over x. When you divide by a fraction, you invert the fraction you're dividing by, and it becomes multiplication. That and that cancel, and you're left with m over m plus x. And that is all you can do. You can't cancel the ones. You can't say, oh, cancel, that's 1. No. Because in the denominator, I have an addition problem, a sum. This is the simplified form, m over m plus x. And as a matter of fact, anytime you have a complex fraction where your numerator and denominator have the same denominator, you can always just cancel it, and you're left with m over m plus x. That only works if the denominators are the same in both numerator and denominator. Number 17, that was 17, sorry. Number 18. So, from what I just said, save yourself a whole lot of trouble. I have fractions in numerator and denominator with the same denominator. Just cancel it, and what are you left with? A over b. It's as simple as that. Number 19. 3 over 5 root 12. A couple ways you can do this one. You can simplify what's in the denominator first, because radical 12 can be simplified. That's 4 times 3. So let's do it this way first. This is equal to 3 over 5 times the square root of 4 times 3, which is 3 over 10 root 3. Now I can rationalize by multiplying by root 3 over root 3, and I get 5 root 3 over 10 times 3, which is 30, and then you can reduce because 5 goes into 30, and I get root 3 over 6. Did I do that right? 10 times 3, 4 times 3 is 12. 2 comes out. 2 times 5 is 10. Then I have to multiply by root 3 over root 2. I'm sorry. I changed the number again. I get 3 times root 3 over 30, which is root 3 over 10. That's one way to do it. I also could have done this. I could have right off the bat multiplied by root 3 over root 3, because that would make my denominator root 36. Which is 3 root 3 over 5 times 6, which is 30, same thing. Equals 3 over root 10, root 3 over 10. Or 1/10 root 3. Again, this and this are identical, and it doesn't matter which way you write it. The only time it might become advantageous to do this, if I had something like this. Or, excuse me, if I had this. Okay, hopefully you would recognize this is 1/10 root 3 minus 1/5 root 3, which then I can say, oh, now I can leave it root 3, and I simply get 1/10 minus 1/5, 1/10 minus 1/5, 1/10, 1/5 is 2/10, so this becomes negative 1/10 root 3. So if you're combining by addition and subtraction, sometimes it might be to your advantage to write it this way so you could see you're adding or subtracting fractions. Okay. The next problem, number 20. 14 over 3 root 75. I would do it this way. It makes it simpler. 25 times 3, which becomes 14 over 3 times, the square root of 25 is 5. It comes out 15 root 3. and then rationalize, multiplying by root 3 over root 3, and I get 14 root 3 over 45. 14 root 3 over 45 is simplified. 14 over 45 is irreducible, no common factors. Okay, 14 root 3 over 45. Alrighty, number 22. 3m over m squared plus 3m plus 2 minus 5m over m plus 1. All right, the only way to combine fractions is if they have a common denominator. This denominator factors into m plus 2 times m plus 1 minus 5m over m plus 1. In order to get a common denominator, my lowest common denominator is m plus 2 times m plus 1, so I'm missing this factor here. In order to get the common denominator, I need to multiply this term by m plus 2 over m plus 2. And I would have 3m minus 5m times m plus 2 over the common denominator m plus 2 times m plus 1. Now, what you need to do is multiply out your numerator and see if you have any common factors, or see if you can factor it in any way. And this becomes 3m minus 5m squared minus 10m all over that common denominator m plus 2 times m plus 1. My numerator becomes negative 5m squared. 3m minus 10m is minus 7m all over m plus 2, m plus 1, and you're not going to have any common factors. The only other thing you could do is you could factor the numerator. You could leave it like this, or you could write this as, I would take out a negative m, and you have 5m plus 7 over m plus 2, m plus 1. Either of these would be sufficient. There's nothing else you can do. You have no common factors in numerator and denominator, so you are complete. Either answer would be acceptable. Okay. That was number 22. And then your final couple of problems, number 28. Number 28. Again, you've got 2 and 1/5 mixed. You've got mixed numbers minus 1/10 x equals 3/15. All right. Again, before I start to solve this one, you should probably change your mixed number into a fraction. 2 times 5 is 10 plus 1. This is 11/5 minus 1/10 x equals 3/15. Lowest common denominator between a 5, a 10, and a 15 is 30. That's 5 times 1, 5 times 2, 5 times 3. So the lowest common denominator is 2 times 3 times 5, or 30. So multiply 30 times the whole fraction, the whole equation. 30 times this. 5 goes into 30 6 times. 6 times 11, 66. 10 goes into 33. 3 times negative x is minus 3x. 15 goes into 30 twice, equals 6. 66 minus 3x equals 6. Add 3x to both sides. Subtract 6. Divide by 30, and you get x equals 20. X equals 20. Okay, and I believe that was your last problem. Okay, that was it. Any questions, write them down, bring them Friday, or give me a call or email me. And I told you there's a lot of geometry review in this book, which we are not going to spend time in class going over. A few things I'll highlight, but I would highly recommend you look them over because standardized tests are going to have geometry on them. They will all be numerical type problems. You're not going to have any proofs on a standardized test. And we do talk about things periodically, like we've talked about with respect to lines. Parallel lines have the same slope, and we also mentioned vertical lines have slopes that are negative reciprocals. And they talk about that in this section. In lesson number 30, they talk about deductive reasoning and vertical angles and a lot of things that we talked about in the algebra or in geometry last year. And I am not going to spend any time really discussing it, but this section had some good problems which I'm going to assign. And the next section is predominantly geometry, with the exception of they do talk again about negative reciprocals. And again, a negative reciprocal, if I have A over B, the negative reciprocal is minus, you turn it over and negate it. So the negative reciprocal of A over B is negative B over A. Another way of thinking about this is any number times its negative reciprocal has to equal negative 1. The product of any number times its negative reciprocal has to equal negative 1. So if I had any fraction, 3/7, the negative reciprocal, turned it over and negated, is negative 7/3. 3/7 times negative 7/3 is equal to negative 1. The product of any number times its negative reciprocal is negative 1. That's why we do not talk about the reciprocal of 0. You cannot turn 0 over and negate it. If you turn 0, that's 0 over 1, I can't say, okay, put it 1 over 0 and negate it. This product does not equal negative 1. It equals undefined because you can never divide by 0. So when I take this, I can't take it. You can't take the product of something over 0. It's undefined. Therefore, we never talk about the reciprocal of 0. We talk about the reciprocal of any non-zero number. And the negative reciprocal of any non-zero number, turn the number over and change its sign. So if I start with a negative, the negative reciprocal is positive. If I start with a positive, the negative reciprocal is negative. The negative reciprocal of negative 2/7 is positive 7/2. Negative 2/7 times positive 7/2 is negative 1. The product of any number times its negative reciprocal must equal negative 1. And negative reciprocals, we talked if line L and line M are perpendicular. If two lines are perpendicular, that means that the slope of line L is the negative reciprocal of the slope of line M. Perpendicular lines have slopes that are negative reciprocals, with one exception. If you have vertical and horizontal lines, hopefully you remember a horizontal line has a slope of 0, a vertical line has no slope. A vertical line is said to have no slope. It's undefined. Because if you remember your slope formula, change in y over change in x, if all the x's are the same, then there is no change in x. The change is 0, which means you would have 0 in the denominator of the slope formula, change in y over change in x, and you cannot have 0 in the denominator of any fraction. It's undefined. So this is true for all lines except vertical and horizontal. They are perpendicular, but their slopes are not negative reciprocals because we don't talk about the negative reciprocal of 0. Okay? And so in sections 30 and 31, really, they don't give you a whole lot of new information. They do also, however, talk about a little bit more about something like this. 2 over root 5 plus 5 over root 2. I cannot combine these as they stand, but I could rationalize the denominator in each case. So I get 2 root 5 over 5 multiplied by root 5 over root 5 plus, here I need to multiply by root 2 over root 2, and I get 5 root 2 over 10. And in this particular case, I can't combine yet because I don't have common radicals. Root 5 and root 2 are different, so that would really be all that you could do in this problem, rationalize the denominator. But if you had something that looked like the following, you could go further. 2 root 2 over root 7 minus 5 root 7 over root 2. All right, now, in this particular problem, when you rationalize, you get 2 root 2 over root 7. You need to multiply by root 7 over root 7. And here you need to multiply by root 2 over root 2. And I get 2 root 14 over 7 minus 5 root 14 over 2. I can combine these because they have the same radical. Radical 14, radical 14. So what I'm going to get is 2 sevenths minus 5 halves root 14. And then you just combine those fractions by getting a common denominator. So you get what? You would get the common denominator of 14. So I need to multiply that by 2. So I get 4. Here I need to multiply by 7 minus 35 root 14. 4 minus 35 is negative 31 over 14 root 14. Kind of sloppy, I'm sorry, but that's the process you would follow. So you can only combine radicals if they have the same radicand, same number under the radical. And in that first one I gave you, you were stuck at the end of just simplifying. Here I can rationalize, and when I rationalize, I get the difference of 2 radicals that have the same radicand. So you simply leave the radical alone and you combine the numeric numbers in front, and in this case I get 2 fractions, 2 sevenths minus 5 halves, get a common denominator and combine, and this one turns out to be negative 31 over 14 times the square root of 14. Okay, so not really anything totally new from these 2 sections, but they have some good problems, and I'm going to give you an assignment for this Friday. Please, from lesson 30, do the following numbers: 3, 4, 13, 15, 19, 21, and 23. From lesson 31, please do numbers 2, 3, 5, 8, 13, 16, 17, and 18. Okay. I hope you all have a great week. If you, again, run into any questions, as always, bring them with you Friday, or call me or email me if it's something you want to know right away. Have a wonderful week. I will see you on Friday.